Okay, hello everyone. Yes, I'm Serdar, I'm the Developer Relations Engineer in IBC at Interchain. Yes, today I'm talking about how IBC meets rollups. This is going to be more about the actual practical applications that are doing this currently and what kind of problems they are facing and what kind of solutions they have proposed to these problems. So the reason why I'm doing this is not because these solutions are correct and are the only way to go, but because this will, first of all, help you understand IBC better and the kind of challenges that we face. And number two, it also helps you understand the problems and maybe come up with your own solutions. And yeah, I think, yeah, we can go. So today we'll cover 4 things. 1, IBC and optimistic rollups. So I'll talk about how IBC kind of works and how optimistic rollups kind of works. And from that, we should be able to see some of the difficulties already. And then we'll look at finalization delaying middleware and escrow IBC, which I think is very interesting, especially escrow IBC, because it can help you bypass the fraud window. And I think that will be very interesting to many of the applications. And finally, conditional clients. I think Aditya talked about this a little bit, but I will also mention that to highlight some open research areas and some of the places where other people can contribute as well. Okay. So yeah, IBC at its core is a protocol for peer-to-peer blockchain communication. So what that means is we are not relying on any oracles or third parties for the blockchains to communicate. I put there that relayers are simply required for liveliness, and because that's the case, we don't actually need relayers' trust in any step. So yeah, that was one of the questions I think earlier as well. IBC's modular infrastructure basically allows people to abstract away some of these things. So IBC wasn't built with necessarily Cosmos SDK or Tendermint in mind. IBC could work with any kind of ledger. And actually the implementation maintained by the core team already supports solo machine clients and most recently the Polkadot parachains. But in general, it can support any ledger. So in this case, the rollups will just be another kind of ledger. And yeah, in this talk, we'll get into some of the rich packet semantics and also how they are used in some of these solutions that I'm going to mention. So difficulties with integrating optimistic rollups to IBC is, number 1, the long fraud-proof window, right? So it's not a good user experience if the user has to wait like 7 days or whatever the fraud window is in order to receive their tokens or other kind of messages. Number 2 is, possibly different DA layer and execution layer. So that means you are potentially dealing with like 3 ledgers in order to actually communicate with the rollup itself through IBC, because we would like to verify everything on chain. And finally, centralized sequencer. It's not only a problem in terms of like censorship, but there's also the problem of antagonistic centralized sequencers in order to trick IBC, right? So we also have to have some defense against that. So these are the 3 main difficulties with integrating optimistic rollups, but those are not the only difficulties. Okay, so before I talk about the finalization delaying middleware, I want to talk about the model of IBC interoperability we have for this current middleware. So here we have rollups and the hub and the other chains. The reason why I called this hub Dimension Hub is because I wanted to give them credit for this middleware. We have like talked to them extensively about developing this middleware and also implementing it, but they finally have a proof of concept, so it would be good to give them some credit. Yeah. So the model we have here is that the rollups have their settlement in the hub. So the hub essentially has already some way of checking fraud proofs in this case. So it doesn't need to be built into IBC. So the hub, we are assuming, does that. And then the rollup communicates with other chains, such as sending tokens through that hub. Because IBC, you can first send your tokens to the hub and then transfer them to the other chains. So this is the model we have. Yeah, so we have some assumptions, and we also need to look at why we want this middleware, which are the consequences. So yeah, number one assumption is the hub has its own module for verifying fraud proofs. Number two assumption is that there's an optimistic IBC-like client between the rollup and the hub. So so first of all, this middleware only deals with the connection between the rollups and the hub, because we are assuming that the connection between the hub to the other chains will be trivial. That means the hub itself is its own sovereign chain maybe, or a Cosmos chain, or a Tendermint chain, or some chain that already has connections to other chains. So this middleware is only going to work for the connection between the rollup and the hub. The optimistic IBC-like client means this. So we are assuming that if the sequencer wasn't cheating, then we would be able to verify packets. So that's what I mean by an optimistic light client. So optimistic light client basically assumes that the opposite side is always correct. And the hub must support asynchronous acknowledgements. I will get into that later, so that's like another rich, I guess, IBC feature, but we don't need to know what that means right now. And the reason why we want that is, number one, the packet inclusion and exclusion can be verified during the fraud window. This is a soft verification. We'll come to that, but at least during the fraud window, you can verify them. Yeah, the fraud handling logic is pushed to the application layer. So a lot of the other talks mentioned how you can use light clients to secure rollups, but in this case, we are actually going to push that fraud logic to the application layer. And we can do that because IBC's very modular structure allows for basically writing middleware that can handle these fraud proofs. Yeah, and finally, if you already, quick to integrate if you already have an optimistic light client, right? So, for example, if your rollup is running Tendermint, this could happen, or some other infrastructure that already has some kind of light client, then this will be very quick to integrate. You don't need to write a new light client. You don't need to worry about all the other things that can go wrong, because you already have the light client that handles some of the misbehavior that can happen. Yeah. Okay, so before I actually explain these steps and how they might be reverted, let's just look at how IBC works normally without having fraud proofs. So in that case, what would normally happen is, imagine that rollup is a chain and that dimension hub is another chain. What would happen is a user would send a send packet message to the rollup that would get committed to its state, and then the relayer would pick that up through events and then submit that packet to the other chain, and then the other chain would process the packet and then commit an acknowledgement, which would then be picked up by the relayer and submitted to the original chain. So I hope this makes sense. There are other things that can happen, right? Obviously, there might be a case where dimension hub is turned off or somehow can't receive the packet. We will also look at that later, but this is the good case. So what does the middleware do? We don't really need to understand what a middleware is to understand what we are doing, but the idea is that the middleware sits somewhere in the middle inside dimension hub, and it can delay some actions, and that's what it does. So yeah, so first of all, let's say you receive the packet, but you don't know that it's going to be, whether it's so you first of all verify its proof with the optimistic IBC light client, and in the next step, you don't know whether or not that packet was actually within the fraud window. It was a fraud, basically. So what the middleware first of all does is it picks up the packet and maybe executes some logic, and then it doesn't finalize it. So it doesn't actually commit the acknowledgement. And then we wait for the front window to pass before we can put the acknowledgement in. So notice that here we didn't actually need to write any new light client. This is only in the application layer. And we will commit that acknowledgement once the fraud window passes. And the way we know that it passed is because the dimension hub, or the hub itself, already has a module for that. Right, so the same thing happens in the other direction as well. So let's say you want to send the packet from the dimension hub to the rollup. What you do is you send the packet, and then the packet is received by the relayer, sent by the relayer. That step doesn't need to be delayed at all because we're assuming that the hub itself is a sovereign chain, so it's finalized correctly. And then number 3 is relayed after the rollup puts an acknowledgement, but the acknowledgement's finalization is delayed. So the hub doesn't actually trust that was actually relayed to the rollup until the front window passes. Yeah, so in the case of a timeout, what happens is, let's say you send the send packet message to the rollup, so you're trying to send a packet from the rollup to the dimension hub, and then the dimension hub never receives it, so the relayer with a proof sends a timeout message. And this one doesn't need to use the middleware at all, right? Because, again, the proof that the packet wasn't included in the dimension hub is a tendermint proof or some other kind of mechanism where we don't need the fraud window. And in the final case, we also have to do the same thing for the timeout on the other direction, but this time we can't trust the message timeout until the fraud window passes. Yeah, so before I move on with how we can actually use this in practice and bypass the fraud window even, I want to see if there are any questions about how this whole thing works. Okay. Yeah. So that whole thing was so that we could delay certain steps until the fraud window passes without necessarily having to write a new light client. That was the whole purpose of that middleware. And that only works when you have a connection between the settlement layer and the rollup itself. But as I said, waiting 7 days for the packet to pass is not good user experience. So what might be a solution to that? And that's where escrow IBC comes in. So before I explain what it is, again, I want to state the assumptions and the consequences of this. So the first assumption we have is that we are dealing with the transfer application. So this escrow IBC model is only built for fungible tokens. And for other kind of IBC applications, we need to have other mechanisms to bypass the fraud window. Yeah, this also requires liquidity providers on both on the chain that the rollup is communicating to, in order to bypass the fraud window. Because we can't really bypass the fraud window. As we'll see, what we can do is move the risk to somewhere else. And yeah, it requires liquidity, and I will get to what that means as well. And as a consequence, from the perspective of the user, the fraud window is bypassed. So what that means is, the user sends the token and they immediately receive it on the other chain. And yeah, the IBC security is not compromised. Okay, so let's go through the escrow IBC flow. So in escrow IBC, it works in the rollup. It starts in the rollup. In step 1, you would send a send packet message to the rollup that basically says, I want to send X many tokens to the dimension, or withdraw X many tokens. And then the relayer again relays the message to the hub, which is in step 2. Yeah, so when that happens, because of the middleware or any other setup you have, we are basically locking these tokens and we are not moving them until the fraud window is bypassed. But we can have a set of liquidity providers that are basically just users that run their own full node off-chain perhaps, or maybe they don't even run their own full node, but they should. They run their own full node and verify that that transaction that happened was actually valid. But they do it softly, right? So, because they didn't wait for the fraud window, but they have that full node that actually verified it. So because of that, they actually transfer the funds to the user immediately because they know that the transaction was correct by running their own full node off-chain. And by doing that, basically, once the fraud window is bypassed, they will receive those tokens instead of the original user. So this way, we can actually bypass the fraud window for the transfer application without actually compromising security. Again, for this, I want to give the credit again to the Dimension team as well. I think they wrote the original paper on this. In that design, you can also assume that the relayers themselves are running are the liquidity providers, although that doesn't need to be the case. you can also add some sort of an incentive structure in order to incentivize people to do this. But this is the core idea. Right, but then the problem is how do we deal with other applications, right? Because this only works for transfers because it relies on the fact that transfer packets have a value that's very quantifiable and they're fungible. So this is still an open research area, so I'd like to hear your opinions if you have any idea on how to bypass some of these or move the risk to another party. So maybe, for example, like for NFT transfers, right? This is also an important use case. You could imagine, because they're non-fungible, I guess you could just mint them on the other chain and then just delete them once the fraud window is, if there's a fraud, right? Because you couldn't do that with fungible tokens, and the reason for that is fungible tokens are fungible. So you can't tell which 5 you should delete, but with NFTs you don't have this problem. So this is a potential solution, but it's maybe not ideal. Interchain accounts, this is also another good IBC application. I think we have another talk coming up later that will talk more about the various IBC applications we have and why you might want them. But with interchain accounts, basically you can control accounts on other chains. And this is like a very well specified feature in IBC. The problem with this is you can't really, bypassing the fraud window for this is really hard, as you can guess, because you're starting to pass general messages. I guess one thing you could do is if the interchain account is controlled from one chain by a user, by an externally owned account, then you could perhaps maybe include a signature in there and you could check that signature so that the user really wanted it. But it becomes much more complicated when you come into non-externally owned accounts taking interchain account actions. And that's where a lot of the use cases today. So we don't actually have a solution to this. Same with smart contracts. Then you're starting to pass general messages, but is there really a way to bypass the seven-day fraud window or however long that is? And that might depend on your actual application. And finally, IBC oracles and ICQ. So I think I should just combine these two ICQ because IBC can be used to maybe build oracles, but IBC doesn't use oracles, so maybe that can be a confusing term. But ICQ is basically, you can query the other chain's key value store without sending a transaction to it. So that's the main value of ICQ. And again, that also is subject to the fraud window, at least on one direction, right? You could always, the rollup could always query the hub, but not the other way around, without waiting for the fraud window to pass. Okay, so everything we talked about so far was in the application layer, and I think there are other solutions as well that we didn't talk about, but I think I will be happy to talk about these if you want to talk to me after the presentation. Instead, I just want to go to the transport layer again and look at some of the ideas behind conditional clients. And this is more of an open research area. The reason why I'm mentioning this is because some of you might be interested in this and might want to understand the things we are thinking about. So this has a different model of, this assumes a different model of rollup interoperability. This time we are not doing a hub, using a hub to connect the rollup to the other chains. Instead, we kind of want to connect the rollup directly to the to chain B, and the settlement layer can be on a different chain. And the rough architecture is probably something like this. So where you have a rollup and another chain where the settlement is, and then you need to relay messages from the rollup to chain B. But for that, you might need two IBC connections, one between the rollup and chain B, and then between layer 1 and chain B. As we'll see, this IBC connection between the layer 1 and chain B doesn't need to be a full IBC connection, but I think this just makes it easier to understand. So what's the goal here? The goal here is to basically have the other chain directly communicate with the rollup and not go through a hub. I think that doesn't necessarily improve the security assumptions actually, right? Because even when you go through the hub, if the hub is the layer, settlement layer, then it's not clear that whether or not this is actually improving any security. But it might be harder to build an IBC client between, this is good for the cases where it's hard to build a IBC connection between the layer 1 and the other chain, in this case chain B. So yeah, that's right. Yeah, so again, you are benefiting from the security of the underlying layer 1 with conditional clients. And finally, yeah, the same settlement, the settlement light client can be shared between multiple rollups. So that's the nice thing about this as well. Yeah, so I guess you could build, conditional light clients in a couple ways, right? So one is maybe you have a rollup IBC light client, a rollup IBC light client, and you have a layer 1 light client, and then they have a pointer to that light client. So so that when you have a packet, you need to pass a verification through both of these. So that's sort of one thing you can do. Another thing you can do is you could this is, I guess, this would be, without any changes to IBC, this would be like, I guess, one of the ways we could do it, right? You could have an IBC light client for the rollup, and inside you have a layer 1 light client. And this layer 1 light client doesn't need to be a full IBC light client in this case, right? Because what we can do is it might just be enough to track a specific header and not the whole header. It might be like, here maybe you can optimize the layer 1 light client more. So, and I think there are also other architectures you can have in between these two, but I didn't have time to explore these and what people are doing with these. Yeah, so I guess there's some open research topics as well, like IBC light client with ZK validity proofs. In that case, you wouldn't need to necessarily have the fraud window, but I haven't seen an implementation of this yet, so that's an open research area. Atomic IBC is a very interesting research area as well. So let's say you have multiple rollups that are secured by the same settlement, and you want to make sure that maybe you want to send multiple packets, but you want to make sure they're executed atomically between these. This is even an open research area in the Cosmos ecosystem currently. So there's some research into it, but it's not even implemented in the current IBC implementation we have. And yeah, shared sequencer network. So all this time we're assuming there's only kind of one sequencer. And when you have shared sequencer networks that secure multiple rollups, that can also play into IBC, that can also play into atomic IBC and other improve other security assumptions. And yeah, bypassing the fraud window for non-transfer applications. This is a big research area. I think it would be good if we could have more applications, still preserve the security, but actually at least reduce the fraud window, even if not bypass it completely. Yeah, I guess it's gone. Did I do that? No. It's okay, I was about to end it anyway, so I'm happy to thank you all for coming. I know I welcome all of you to Istanbul, especially all of you who came from very far away places to the city I was born in. So yeah, that's it. I'm happy to take questions.
Thank you. Maybe it was so obvious, but I missed. But in order to provide the liquidity to secure the operations of the escrow, I assume it all should be in the specific token type, right? So who will do that? Why would they do it? Or how much token would be enough to protect the whole network or the protocol?
Right. So those tokens are not required for the security, right? It's only required for the speed of the transaction, because let's say if there are no liquidity providers stepping up, you could still just wait the 7 days or until there's a liquidity provider that wants to step up to the speed of the transaction. So how much would be required completely depends on how much both chains are used. So I don't, and there is no current implementation in production yet, so I don't actually have the numbers. We don't actually have any numbers on how much would be enough. The way you would initially get those tokens there is actually by IBC transfer itself. So liquidity providers would start at one chain and actually just do a normal IBC transfer of some tokens they have on the other chain and just wait for the fraud window to pass, so that now they have coins on both sides and they can, they have coins on this side and they can just provide these to users quickly. So the way you would get the tokens in the first place is actually doing the IBC and waiting for the fraud window to pass. Yeah. Does that answer the question? Okay. Yeah, for sure.
Any other questions? All right. Well, thank you so much, Serdar, for the presentation.